Okay, so welcome everyone. We are very happy to have Ivano Basile here today to give us a seminar. He was supposed to visit in person, but unfortunately it was not possible in the last moment. So I hope that we can make this talk as interactive and lively as possible and try to pretend that we are there all in person at the IFT. So he's coming from the University of Mons, and he will talk about emergent strings in a finite universe. So whenever you are ready, please, Ivano, go ahead.
Okay, thank you very much, Irene, for the very kind introduction, and I completely share your sentiment. I am very sorry that I couldn't come in person because of COVID, obviously, and so I apologize in advance that you may hear some coughing, intermittent coughing during my presentation. I hope it's not too much of a bother. But surely it's better than having me cough right there at the IFT. But yeah, as far as making the seminar as interacting as possible, please feel free to ask questions and interrupt me at any moment. Yeah, there it is. So so the title of this talk already includes some hints on how what it's going to be about. It's going to be about emergent strings in the sense of the emergent string conjecture, of the distance conjecture, and ideas of that type. But it's also going to be about this keyword finite universe. What I mean by that is some particular scenario that occurs in string theory where supersymmetry is broken at the string scale, and the universe essentially closes off in a finitely extended direction. And I will delve into more details later. And all of this discussion about what happens in string theory with broken supersymmetry is very much tied to ideas regarding the swampland problem, and which is why I'm represented both a landscape and a swampland coming from both from Spain actually. So this discussion would be very much about swampland ideas and how they tie into particular non-supersymmetric swampland, non-supersymmetric landscape that we found and studied. And here, if you want some references, you can search for these archive numbers. All right, so to begin with, I'm going to lead with some motivation. Of course, the necessity to study supersymmetry breaking in string theory, in quantum gravity in general, is doesn't need that much motivation because it's clearly needed for phenomenological purposes and also to better understand the theory itself. However, there is a point that I would like to make as for the specific kind of supersymmetry breaking we should study and look for. So first of all, very naively, from dimensional arguments, if we start from our beloved perturbative string theory, there is only one dimensionful scale, which is the string scale. So barring particular fine tunings of fluxes or couplings or etc., really we should somehow expect the supersymmetry breaking scale to be of the order of the string scale. This is what the bare high energy theory points to, in contrast with the usual low energy supersymmetry breaking constructions that litter the the landscape of attempts. And also, I would like to mention that some people, including some that are part of this audience, have proposed and studied a particular swampland criterion that involves the gravitino, particularly the mass of the gravitino. And the idea, one of the implications of this gravitino distance conjecture, if you will, is that essentially the supersymmetry breaking scale cannot be made parametrically small in a consistent way within the effective field theory, right? Which means that if this is true, there is no effective field theory of supersymmetry breaking. That would be the punchline, right? So what we would be left with is the alternative of studying string scale supersymmetry breaking, right? So this is why I'm going to focus on these kinds of models.
Ivano, one question. So why string scale? I mean, with these conjectures, doesn't need to be so high, right? Or
right. The conjecture itself just says that the scale cannot be parametrically low. So in principle, you could have some, 10 to the minus 100 times alpha prime or something like 1 over alpha prime. So you could absolutely have numerically small scales, but not parametrically small. What I'm trying to say is that usually, right, if you can construct sufficiently numerically small things, it's because you have some freedom with some parameters, some discrete fluxes or stuff like that. And somehow the most natural thing to do first, before doing that, is to look at order 1 in the string scale. That's what I'm saying essentially. Like, given that we cannot go arbitrarily low, might as well try 1 before going to 10 to the minus 100, because that's not even clear that we can do that. Right? This is a bit reminiscent of the situation of flux superpotentials, right? Where the Cornell group found these explicit constructions with numerically very small potentials, but somehow the parametric limit, as far as I understand, is still not reachable. But I think it's good enough for many purposes. Okay, so so this is essentially the plan of the talk. So I'm going to start by reviewing the non-supersymmetric models that I'm going to talk about. So they are string models in 10 dimensions where supersymmetry is broken at the string scale in various senses. So it's either absent from the get-go or it's spontaneously broken. It depends on the model. Then I will move on to investigate the consequences of supersymmetry breaking, essentially on the vacuum itself, right? And I will try to build a consistent or a consistent looking landscape of vacua for these models. First, from the point of view of effective field theory, and then understanding when this effective field theory gravitational description breaks down, right? And this will lead to many, many connections with various swampland conjectures in a sort of novel roundabout way, not the usual realizations of these conjectures. And then in these regimes where the effective field theory breaks down, I will describe the stringy description of the physics using mostly the dynamics of branes. And this essentially gives us the hope, if this description works and is consistent, that perhaps, although the low energy effective field theory turns out to break down spontaneously, if you wait long enough, instabilities will drive it to a stringy regime, maybe the theory still remains consistent in a stringy regime, which cannot be described by the low energy effective field theory. And in particular, I will focus in the final section on some new results concerning infinite distance limits, where a variety of distance conjectures are realized when looking at this very stringy regime. So this is the plan. So I'm going to, well, I'm going to also, as I anticipated, get to some realization of various swampland conjectures. And in particular, I wanted to mention these ones, the most important ones that arise. So first of all, we will immediately encounter the de Sitter conjecture, the obstruction to de Sitter vacua in the form of compactifications. And I will also mention a way to go around the absence of compactifications via brane world cosmologies that do arise in these models. And then we'll see that the weak gravity conjecture plays a central role in all of the dynamics of this landscape, because essentially the vacua in this landscape are unstable, and their decay is driven by the gravity conjecture via repulsions of branes. And the reason why these branes repel turns out to be quite non-trivial in these models. And then this repulsion and these instabilities lead the theory to infinite distance limits, where the distance conjecture turns out to work even without supersymmetry in a generalized sense. So I'm going to now get into the thick of it. So I'm going to describe these non-supersymmetric models. All right, so these are 3 10-dimensional models, as anticipated, and they come in 2 families. So 2 of them are orientifold models, and in particular, they are orientifold projections of the type 2b string and the type 0b string, as you can see from this extended duality network. While the third model is a heterotic one. It's perhaps the more familiar of these broken supersymmetry models, which is the SO16 cross SO16 heterotic model. So these models have certain gauge groups which don't really matter for our purposes. But the key point is that either projection, so all of these models arise from projections, and what the projection does is either introduce some O9 and anti-D9 combination in spacetime, or it introduces a non-vanishing vacuum energy in the case of the heterotic model. So both of these elements are sources for dynamical tadpoles, right? Either because the combined tension of O9 and anti-D9 branes, or because of the vacuum energy itself. Essentially, there is an effective potential that is generated at the first non-vanishing order, the leading order, and this causes all sorts of problems. So concerning these models, in the low energy effective field theory, the only thing we really need to know is the emergence of this potential caused by this dynamical tadpole and the brane or flux content of the theory. And then when going to the stringy version, we will need some more microscopic information, including the gauge groups. So before moving on to the low energy effective field theory description, I wanted to mention an important point about one of these 3 models. So it turns out that this particular model, the type 2b orientifold, breaks supersymmetry in a particular way compared to the other ones. And the way that it breaks it is by keeping it in the closed string sector, while breaking it on the D9 branes, the anti-D9 branes, so the open string sector. So this is a particular situation that leads to essentially a spontaneous breaking of supersymmetry, in the sense that the massless spectrum contains a Goldstino fermion. And it has been shown that this Goldstino fermion has the correct low energy couplings to describe a spontaneously broken phase of the theory. And in this sense, it should be able to be described by a nonlinear supergravity, right? Compared to the other 2 models, where just the supergravity description is just to be abandoned completely. It's just a gravity theory. In this case, it should be possible to describe a nonlinear supergravity, but this has not been done so far because of the difficulties in handling nonlinear supersymmetry in 10 dimensions. But I did want to mention this important point. So other than that, again, the most important ingredient that we need is this exponential potential for the dilaton that is sourced by either supersymmetry breaking element in each of these models. So this T is either the residual tension of this O9 plus anti-D9 branes, which is non-zero in these models, or the vacuum energy, the torus amplitude of the heterotic model. And accordingly, this exponent gamma changes depending on the theory. This is the Einstein frame potential. And this potential, as you can immediately see, completely destroys the flat space perturbation theory, right? Because there is no flat space solution anymore. And this means that there is a sizable back reaction. Although these models have no tachyons, there is a back reaction driven by the dynamical tadpole. And the problem is that this T number is of order 1 in string units, which means that if left alone, this back reaction, whatever that is, will be of the order of the string scale, which means that the effective field theory completely breaks down, right? So this is the crucial problem. So how do we deal with it? And how do we construct a consistent looking or controlled landscape where to actually, study the physics? Well, many various approaches have been proposed in the past, changing up the models and working with different kinds of non-supersymmetric projections. But somehow, this T number, essentially, or this exponent gamma can be changed, but this effect can never be eliminated completely. So we rather took a different approach. And this approach is to introduce new parameters, not to change the model, but to change the vacuum, right? To work with vacua where there are branes and fluxes, essentially. And this allows us to use a new control parameter, which is just the number of branes that we put in the vacuum, right? And it turns out that for large values of this parameter, things can be controlled in some sense. So this is what our plan for the low energy description of our non-supersymmetric landscape is. We start from our low energy effective field theory, which is basically the usual one as far as the bosonic sector is concerned, except for this tadpole potential, this exponential tadpole potential. So this is the key difference compared to the supersymmetric cases. And another difference is that the fluxes that are present are not are a bit less than the usual models that one considers. So in type 2 strings, in type 2 supergravity, there are many more field strength that one can include in the action, one can turn on in the vacuum. In these three models, it turns out that there is only one free-form flux. In particular, it stems either from the Ramond-Ramond sector in the orientifold models, because the NS free-form is projected out, or in the heterotic model, we only have the NS free-form, and we don't have any Ramond-Ramond sector. So in either case, we only have one free-form with a specific Einstein frame coupling to the dilaton. So this alpha value here is fixed depending on the model. And then, this in the orientifold models, this Ramond-Ramond free-form sources D1 and D5 branes, whereas in the heterotic model, it sources MS5 branes. And these turn out to be the easiest branes to deal with, which is why I included this term in effective action. And this is what our main focus will be. I will briefly mention what happens in the 0B orientifold, which is called 0'B model, because this model also includes charged D3 and D7 branes, which couple to, to the self-dual 5 form, right? And so I will briefly mention what happens in that case, in the case of D3 branes, but will not be the focus because it's a little bit more complicated. So this is the low energy description. And I'm now going to describe, how we get to a sensible landscape of solution, because recall the original background we would have liked to start from flat space is not there. So we need to look for more general, more complicated solutions. So what's the first thing we can look for? Well, we can look for warped flux compactifications to a maximally symmetric spacetime, right, of a reduced dimension. This is the first thing one can try to do. And it turns out that despite this vacuum energy contribution being positive, we managed to prove a no-go theorem, which generalizes the known no-go theorems in supergravities, whereby the sign of the cosmological constant of the resulting spacetime is fixed by the parameters in the theory. So this Q is the dimension of the compact space. And it turns out that this combination is always negative in our models. So we can only have anti-de Sitter compactifications, even with warping. And so this is our first encounter with a swampland criterion, because the way in which de Sitter solutions are prohibited in these models is not, just that they are prohibited; they are obstructed by an order one, barrier, precisely in the sense of the de Sitter conjecture. So we were able to prove that this bound holds for the effective potential of the dimensional reduction, determining this particular order one constant. So the de Sitter conjecture does hold precisely in these models. So what's left now? Well, we can look at anti-de Sitter-like solutions, right? So how do we build anti-de Sitter solution? Well, now I'm telling you the story in reverse, but it's clearer to think about anti-de Sitter in this case, usually as a near horizon throat arising from the geometry source by a stack of branes, right? Obviously, one can just look for an ADS times some compact manifold as a solution, and one does find such solutions, but it's more useful for us to think about them as near horizon limits. So the first thing to do is to determine the full profile of this geometry source by branes, right? And to do this, absent the usual supersymmetric integrability properties, we have to solve the full-blown Einstein field equations. That's the only thing to do. So what we did was impose the isometries of such a configuration with a stack of parallel branes, and this is the most general ansatz to write in a suitable gauge. And here you see that the flux contains the number of branes, right, in some units. So with this ansatz, the final equations are not only not integrable, they are completely untreatable. They are so nonlinear because of this exponential potential. And so what we managed to do was find the asymptotic solution near the horizon and far away from the branes in these two regimes. And then we patched them up numerically. But this is not the interesting part. The interesting parts are far away and close to the branes. So close to the branes, we did indeed recover a solution that looks like ADS times S in the precise case of parallel branes. As you know, if familiar from the supersymmetric cases, if the branes are put on a conical singularity, the sphere will be replaced by something else. So indeed, there is the possibility to change the sphere to something else. But the solution looks essentially the same. So this is ADS times S written in weird coordinates. And this L and R are the curvature radii of the ADS and S parts. And it turns out that they are fixed to some power of n, which is positive, which means that for large number of branes, the curvatures are small in string units. And this is completely familiar from the supersymmetric case. Think about the ADS 5 times S5 solution sourced by D3 branes in type 2b. This is completely analogous, except that the power is different. Now, what is not analogous is that the string coupling e to the phi is constant, but it's not a modulus. It's also fixed by n to a negative power, as it turns out, which means that not only we can tune it to be small, but we have a parametric smallness in the same limit as we have a small curvature regime. So for large n, we get the two perturbative limits of string theory essentially for free, which is very encouraging. It gives us a handle on this landscape of ADS near horizon limits. And indeed, we also showed that this solution arises as a proper near horizon, in the sense that if you perturb away from the horizon, there are some perturbations, some modes that either die out, that are attracted to the horizon, or they blow up. And this is completely analogous to the supersymmetric cases, because essentially there are conditions at infinity that need to be fine-tuned in order to flow into a near horizon throat. And these conditions are BPS bounds. So you take the asymptotic charges, so the ADM tension charges and whatever, and you tune them to satisfy BPS bounds in order then to flow to a near horizon throat instead of a event horizon, like to a Ringler geometry. And this is precisely analogous, except that in this case we don't have the full geometry to test this. What we can do is to match the number of parameters to tune to flow to a near horizon, which is 2, as it turns out, to the number of free parameters in the faraway region, which is also 2, as it turns out. So we do have this map, right, to go from the faraway region to an extremal near horizon throat. Albeit we don't have the full solution because the equations are too hard. Now, we can move on to this faraway region. But first, let me discuss what happens in the case of D3 branes. So this discussion about ADS times S throats is true in the case of 1 and 5 branes. So either D1 or NS5, actually, not for D5 branes. Either D1 branes or NS5 branes. So one would expect D3 branes to follow the same, to have the same fate and end up in an ADS 5 times S5 near horizon. This is what happens in type 2, right? But it's not what happens here because of the supersymmetry breaking. And what happens instead is that the geometry looks like ADS times S locally, but the supersymmetric values that one would have in type 2b case are corrected by a 1 over n term, which, however, is arbitrarily large depending on where you are in the geometry. So locally, for a given interval of this log u, sufficiently large n gives you an ADS 5 times S5, more or less, approximately. But fix the n, you can go sufficiently close to the throat that this approximation breaks down. So it's locally, it's quasi ADS 5 times S5. So this is the reason why our focus lies in D1 and S5 branes, because their near horizon geometry is much simpler. But we will be able to say something about D3 branes also. So now I can move on to the faraway regime, right? And here something very much exotic happens. So in the case of the near horizon limit, already something new compared to usual supersymmetric cases happens, which is that new ADS throats form where there were none in the supersymmetric case. And not only that, the string coupling saturates to a specific value. So this is a new feature of the near horizon limit. As for the faraway regime, something new also happens, and it's dramatic. So instead of having an asymptotically flat space, as usual in the supersymmetric cases, as I anticipated, there is no such flat space solution to asymptote to. Instead, studying the asymptotic behavior of the equations of motion, turns out that the behavior is such that there is a finite distance singularity where spacetime ends. Now, we found that this property is actually quite universal. So pretty much independently of the type of branes that you put, even for branes that have no charge and no flux, this happens. And this was also discussed recently by Angel and collaborators in two papers that connects this property to the cobordism conjecture, the distance conjecture, and ideas of this type. So somehow it looks like while the finite, the space-time distance is finite, the theory space distance is infinite. So I'm not calling it the moduli space distance because it's not exactly a moduli space, but the theory space, the pseudo moduli space distance diverges at this point. Rather, this is what happens using the effective field theory theory space metric. But it turns out, as I will show later, that even going beyond effective field theory, it looks like these limits are still infinite distance in some sense. So this is the punchline for this part of the talk. So studying the low energy gravitational description, we do find a landscape of solutions, which are ADS compactifications, which are well controlled. But it turns out that going away from this throat, space-time not only becomes non-perturbative, it just flat out ends in a singularity. And this is the picture that we made to describe this. So what happens here is, we don't know. The singularity is well outside of the low energy effective field theory. Now, this is something again that has been discussed by Angel and collaborators, and essentially the claim, if I understand correctly, is that there should be some end of the world defect there that soaks up the cobordism class of the near horizon throat in such a way that total cobordism class vanishes for this background, which is what one would wish, right? Since the cobordism conjecture is so well supported. But again, we have no quantitative control of what's going on there. So this is what happens from the...
Sorry, quick question. You don't have control because you go to strong coupling? Is that the...
You go to strong coupling and strong curvature.
But okay, but then the supergravity analysis that you make should fail, and then maybe something funny happens after it fails, or how do you know?
How do you know? Well, exactly.
Before you get to the end of the world, I mean, you lose control, right? Is that correct?
Yeah, that's the claim.
So is there a chance that something could happen that will take you not to far end of the world? The space-time doesn't end, or?
It could happen. Yeah. So what I meant to say is simply that the low energy analysis tells you that a singularity is there, which means really that in the full theory, something happens and we don't know what. So okay. The theory enters a strong coupling regime at finite distance, finite space-time distance away from the branes, and this is all we know. That's it. It could happen. Anything could happen, and yeah, we don't really know what it is.
Sorry, can I ask?
Yes, of course.
What gets bad first, the alpha prime corrections or the string coupling?
So I would say that they get bad at the same time, because essentially this asymptotic behavior of the fields. So this phi VNB, so phi is the dilaton, and V and B are these warp factors in the metric, right? So they control the curvatures. These guys are asymptotically proportional to the same function. They go, they go bad in the same way. I would say that.
Yes, but you typically have the metric depending on G string n, not just in G string, no? And the dilaton.
In this gauge, actually, the metric doesn't depend on phi at all.
Mm-hmm.
So I'm not sure what you mean. I mean, I agree with you in
You wrote some profile function before with a log of U.
oh, you mean, but this, you mean for the D3 branes?
Yeah.
But this is the near horizon limit actually in this case. So when talking about space-time going bad at finite distance, this is the behavior we are looking at, and you know, all of these functions go with the same profile. So the dilaton stops being very negative in the same regime as these other ones. So if you wish, the exponentials of these guys get to order 1 values at the same time.
Mm-hmm.
Yeah, so this is the punchline of the...
Maybe, yeah, one more question, since this is the punchline. You said also that you would expect to have a defect at this end of the space-time. What is the topological chart that you need to cancel? How you know that you cannot, that the covariance class is trivial already only with the geometry?
Right, so so this is actually the claim of these papers.
Yeah, but sometimes it could be that it's just a geometric thing. You don't need to have a localized effect.
Could be, but what needs to happen is that if the branes are charged, and so they have this throat, there should be, the flux lines should end you know, somewhere.
Okay, so it's the flux that you need to cancel.
Yeah,
and you don't have enough Chern-Simon terms that you could cancel it only with the geometry?
good point. Unfortunately, no, because in these models, the projections are such that those Chern-Simon's term in the low energy actions are removed. That's what happens. So we don't really, yeah. And again, since this thing, this configuration appears to be universal, independent of whether the branes are charged or not. As you say, the kind of charges that this defect should have can change depending on what you put at the other side. So yeah,
that's interesting. So if there are less Chern-Simon terms comparing to the supersymmetric compactifications, I mean, it might be that you can predict the existence of new defects to break or gauge all the global symmetries, right?
yeah, I completely agree. Yeah, I feel like this is part of the message of these papers, and I agree that this is what should happen. All right. So before moving on, I want to give you just one quick example to show you that this construction also covers uncharged branes. And indeed, by taking this family of solutions that we found and just putting p equals 8, which namely means the 8 branes that are not charged, one actually recovers an exact solution. So the solution becomes fully writable, and it coincides with the solution found by Dudas and Murad some 20 years ago, which was, well, if you look at the paper, they called it brane solutions, right? But there is no mention of any branes anywhere in the paper, and we somehow elucidated the situation by showing that these solutions are part of a larger family, which, varying p and the charges, we can include also this solution, which should represent the geometry sourced by the 8 branes. And as was noted long ago, indeed, this transverse direction is finitely extended. All right, so now let's move on to the instabilities of these vacua. I described a landscape, right, with weakly coupled regions. So we're going to focus on the weakly coupled regions. And what happens there? Well, as usual, in non-supersymmetric ADS vacua, one expects instabilities, right? It turns out that the perturbative instabilities don't teach us very much. So they are there, but they can be removed in some cases. I can delve into more detail if you like, but this is mostly a technical thing. I have some backup slides for that. But the more interesting instabilities in this case are the non-perturbative ones, so brane nucleation or bubbles of nothing. And brane nucleation is actually calculable in these models pretty easily. And we found that the branes that nucleate, right, with this decay rate that we calculated, so the decay rate depends on this extremality parameter, right? And normally the extremality parameter is just bare charge over bare tension, right? So the tension that is not dressed by the string coupling. But what happens in this case is that the extremality parameter that enters the decay rate has a very specific form. This is charge over dressed tension times some power of GS times a constant. So this constant just appears in the non-supersymmetric models. In the supersymmetric models, it's 1, right? In our case, it's not 1. And the consistency of this calculation, so the fact that the decay rate should be exponentially suppressed, actually implies a very specific scaling, which tells us that the dressed tension of these branes has to scale with the string coupling in a very specific way. And, and this specific way, if you go back to the string frame, is exactly what you would expect from D branes, 1 over GS, NS5 branes, 1 over GS squared. And also it covers more exotic branes of the type that have been studied by Riccioni, Berkshire, and others some 20 years ago. So the relation depends on this alpha parameter, which I remind you is the parameter that controls the coupling between the dilaton and the flux. So the punchline here is that brane nucleation in these models tells you that these branes are precisely the microscopic branes that we know make up these ADS. So it's not that these ADS vacua just nucleate any weird EFT branes. They actually nucleate D1 branes in the case of ADS3 and NS5 branes in the case of the heterotic model in ADS7. So this is precisely what we expected. And moreover, for large N, large number of branes, these decay rates can be parametrically, are parametrically small, actually exponentially suppressed in N. So we can make these vacua not completely stable, but arbitrarily long-lived and perturbative, right? So this is the best we can hope for with broken supersymmetry. And as a result of this brane nucleation, we also get for free a brane world cosmology, a de Sitter cosmology that an observer riding one of these nucleating branes observes. Right? So this was revisited recently by the Uppsala group in this context of looking for a phenomenological construction, but it does hint to another possibility for decay, which is bubbles of nothing. Right? So this has been investigated by some members of the audience, including Irene, as a possibility for a universal decay channel, right? Because that's what we want. We want a universal decay channel for non-supersymmetric vacuum. So in this case, we have for sure brane nucleation. We showed that it's there, but we also showed that this decay rate can be arbitrarily small. So the question now is, can we make arbitrarily long-lived vacua, or do bubbles of nothing ruin this parametric long life with a decay rate that cannot be reduced parametrically? So this is an open question that we're looking at together with Giuseppe Di Benedetto, and I think it's interesting to see what happens for bubbles of nothing in these models. All right, so this is it for the macroscopic description.
Ivano, sorry, before you continue, I'm a bit confused about the parametrically long-lived ADS vacua. I mean, typically in ADS, if you have some instability, it's going to be at least of order hour, right? Because of the time that takes to reach the horizon and come back.
I'm not sure I understand what you said. So the instability is what?
Of order Hubble scale.
Hubble.
Yes.
Okay.
So I'm confused how you can make it parametrically
Well,
small, the decay rate.
because the key is that I'm guessing what you're calling Hubble is the curvature radius of ADS, more or less. The key is that that radius itself is parametric, has a parametric dependence on the number of branes that you put. Right. So you can make the ADS parametrically flat.
Okay, so it's still going to be a decay rate for the curvature, the Hubble scale, but you mean that you can make this Hubble scale as close to the flat space limit as you wish? But that's also, I mean, you're not gonna have scale separation anymore. Like if you put too small cosmological constant, right?
Yeah, there is
the EFT is going to break down as well, right?
Indeed, and I'm going to talk about that quite soon. And the EFT does break down because in the Kaluza-Klein way, in this limit, and because there is no scale separation, absolutely.
Okay.
I'm so sorry. So now I'm going to move on to the stringy description or what happens. So now, so far we talked about the gravity side of things. So we have this controlled landscape of long-lived ADS vacua. We showed that far away from there things break down in weird and exotic ways. But focusing on the control regime, there are some instabilities that should be describable in terms of brane dynamics, because these vacua are made of branes. And this will suggest a description for the stringy regime. And so this description is not just of academic interest because, well, all of this in some sense is, but if you take these ADS vacua in the large N regime where everything is perturbative and wait long enough, they are going to become stringy eventually because N will go, will become less and less because of brane nucleation. So eventually we will reach the regime in which we need a brane stringy description of what's going on. So a good place to start is the calculation of interaction potentials between these branes in various regimes. And we can check if indeed they repel themselves as predicted by brane nucleation. So you see in brane nucleation, this V0 parameter appears along the externality ratio of the branes. And it turns out that calculating potentials between branes that share the same charge also involves this V0 parameter. So these are probe potentials calculated with probe branes in these ADS geometries. And it turns out that both for D1, D1, D3, D3, and NS5, NS5, because it's the same formula, except this is a 6. In all of these three cases, which are the cases where we can actually calculate this interaction, these potentials do not vanish like the BPS case. So these branes are extremal, but they're not BPS in the usual sense because of supersymmetry breaking. The supersymmetry breaking introduces this V0 term in such a way that it's not 1 plus minus 1, it's 1 plus minus something that is bigger than 1. And this is precisely because this V0 is bigger than 1. So it turns out that the weak gravity conjecture is satisfied and these branes repel because of the supersymmetry breaking term. And if you tune that to 0, you get 1 plus or minus 1. Of course, you cannot tune it to 0 because there is no parameter. The supersymmetry breaking is stringy, irreducibly. But it's nice to see that there is the novel realization of the weak gravity conjecture. Now, what one can do is to also investigate other kinds of brane interactions to support this picture that the interaction between these branes are still consistent although supersymmetry is broken. So the remaining probe potentials that one can compute are these ones, this family of potentials, where the branes do not share charges. You see, they didn't have the same charge, so they cannot repel. or rather they could repel, but because of the exchange of gravitational multiplets. And then one can compare these amplitudes, these potentials, with the potentials extracted from string amplitudes. And this cannot be done in the case of equal charged branes, rather cannot be done easily, because the string amplitude calculation for like charged branes is much more complicated, because the leading term vanishes. So one has to look for more complicated Riemann surfaces. In this case, instead, we can take this whole family of potentials and compare between the probe limit and the string amplitude limit. And the reason for doing this is that in supersymmetric cases, comparing 0 with 0 is it's nice that it matches, but it's not extremely surprising, right? In non-supersymmetric cases, we get attract, attract, repel, repel. If we match this behavior, it's a good hint that the interactions of branes is consistent across the various regimes, independently of how many branes you put. And it's non-trivial because there is no protection now, that there is no guarantee that this will actually happen. But if you actually take these potentials and you compare them, it turns out that they do match in character. So they either are repulsive in both cases, so both when there are few branes and when there are many branes that backreact on the geometry, so the string amplitude limit and the probe limit, or they always attract in both cases. And this matching, this non-supersymmetric matching, was completely, unwarranted, but it does occur. And so it looks like it's a pretty good hint that we can at least try trusting this description in terms of branes, even when the description in terms of gravity is unreliable. Right. And so this is what I'm going to do now. I'm going to describe these ADS vacua, this ADS3 vacua in particular, in the stringy regime using branes and the holography. Right. And this will lead us naturally to infinite distance limits. This is the last part of the talk. So if there are any questions, maybe it's a good time.
Yeah, so sorry, you are going to translate these potentials to some holographic quantities, or what is the meaning otherwise?
So these particular ones I used to check that the regime where there are many branes somehow is consistent with the regime where there are few branes, in order to carry over this description to a small number of branes. The holographic calculation that I'm going to show is actually for the case of D1 branes, because they are the simplest ones to treat holographically, essentially. And in that case, the only potential to which I can compare things is the probe potential, not the string amplitude potential. So I'm going to compare this potential with the holographic result, and then move on from there.
One question on page 19. Hi. You had this picture with these branes and then something traveling in the middle and a blob that's Susi breaking. Is there any meaning to this diagram?
Yeah, of course. So the idea is the following, that absent the supersymmetry breaking, you see these potentials would vanish.
I see.
So the point is that the presence of the supersymmetry breaking ingredient, for instance, O9 plus anti-D9, is this mediating effect. So if you draw the actual string diagram, instead of the annulus, you get an annulus with a third leg that ends on the anti-D9.
I see.
And that's what this is supposed to represent.
I see. So the Susi breaking is like an extra source in the otherwise Susi coupling.
Exactly. It's a mediator of the interaction.
Thanks.
You're welcome. I'm glad you could make it. I hope everything is okay.
Yes, thanks.
Okay.
In principle, just so you know, you have 5 minutes left.
Yeah, I
you
have
keep it in mind.
Yeah, I have a timer here, so I'll try to be quick
Okay.
here. because this final part is the most important. I know there have been a few questions. Okay, so first of all, again, I anticipated that the simplest setting to look in the string regime is specifically ADS3 sourced by D1 branes in the orientifold models. This is the simplest setting because the corresponding holographic theory should be the infrared regime of the world volume gauge theory that lives on the D1 branes. Now, this theory is complicated still, but we did manage to make some progress. So first of all, the UV of this theory, which is not the holographic theory, the holographic theory is the IR. In the UV, this theory is asymptotically free, and we can compute the effective potential for separated branes reliably. And a one-loop computation actually shows a repulsive behavior driven by tunneling, and which matches with the proof potential that I described before. So this is the UV description, the UV regime of this gauge theory, but the holographic theory should be the infrared, right? So what do we do to study the infrared? Well, it turns out that infinite distance limits come in handy to study this theory. So, so this theory for generic values of n, the number of branes, has a very complicated infrared because it's strongly coupled and non-supersymmetric. So the only way to make progress is to study limiting cases. So either large n or small n, so n equals 1 essentially. And we should find some holographic version of the brane nucleation that changes the value of n. Right, so well, I don't need really to explain to you what an infinite distance limit is and why it ties into an exponential decay of a tower of states. But I do want to show you this picture. So, sorry. So this picture describes what happens holographically corresponding to the nucleation of branes in ADS. What happens is that essentially there should be an RG flow that connects the corresponding CFTs, because really in an unstable ADS, one is never in a CFT because there is this decay rate, right? And indeed, the proposal is that one is actually standing on this RG flow that is dual to this brane nucleation. And the RG flow can be actually described pretty explicitly by taking this holographic theory and integrating out the separating the brane separation mode has been done long ago for n equals 4. And one finds indeed RG flows that connect these theories. Now, the only explicit cases that one can study are large n and small n, right? And according to the emergent string conjecture, one should find either a KK limit or a higher spin limit, right? An emergent string limit. And this is exactly what we find. And so let me describe very briefly the large n limit, which is, as Irene anticipated, a Kaluza-Klein limit. So in the large n limit, what happens is that the scale separation is absent, right? So the internal space expands and becomes flat together with the ADS. And indeed, calculating the mass of Kaluza-Klein modes, one can show that it's exponentially suppressed in a suitable generalized distance in theory space, in field space, which essentially is the integration of the moduli space the scalar space metric along the profile of these bubbles that separate, that interpolate between each ADS. And while the bubble profile itself is unknown, one can very easily show that there is a bound on both sides such that this thing always, these masses are absolutely exponentially suppressed in the distance, even if we don't know how to compute this integral. So this also actually confirms the ADS distance conjecture precisely because these KK masses are also tied to the ADS cosmological constant. So now let me move on to the final infinite distance limit. That it's the other one, the n equals 1 limit. And this is a very stringy limit because there is no large curvature or small coupling, right? So the only reliable, expectedly reliable description we have is the holographic description. There is no bulk description here. So hopefully we should find that this particular stretch of the RG flow somehow is an infinite distance limit in the holographic theory, and we should find the emergence of an infinite tower of higher spin currents in the holographic theory, if this is true. And indeed, this final stretch can be described pretty explicitly. So again, by integrating out the brane separation mode in the gauge theory that lives on two branes, right, we find a nonlinear sigma model description of this CFT, and integrating out this brane separation turns out to be described by essentially what I would call a graviton vertex operator deforming the nonlinear sigma model. And we can follow this RG flow pretty explicitly in this infrared regime. And in this infrared regime, we can compute the distance along this RG flow defined as a generalized zamologic of distance, essentially the one that was recently revisited by John Stout, but was actually proposed long ago by O'Connor and Stevens. So this metric along the RG flows is a generalization of the zamologic of metric, and it can be computed in this particular case, in this last stretch of the RG flow. And recall, if this last stretch is at infinite distance, all of it is at infinite distance, even if we cannot compute it. And indeed, it turns out that only in the case of D1 branes, so in the case of a string, this limit is at infinite distance. And what's the final limit? Well, so this final theory, so this CFT corresponding to a single brane, should have an infinite tower of higher spin currents, right? By this logic. And indeed it does. Not only that, but it has essentially a completely decoupled free sector corresponding to some scalars and fermions. And it just so happens that in the type 2B orientifold, so the spontaneously broken one, supersymmetry is recovered in this final state because this decoupled sector reconstructs a minimally supersymmetric multiplet. And the reason why this happens is because of spinate triality, because these guys, these fields, are in representations of spin 8, because these are D1 branes in 10 dimensions, so they have 8 transverse dimensions. And again, this only happens because this is a string, right? So you see what's going on here. There is a conspiracy that makes this infinite distance limit with emergent supersymmetry only happen because of this coincidence of factor. This is precisely the emergent string conjecture. This infinite distance limit could only happen with a string and not with a higher dimensional object. And this happens because of this, these coincidences. And in addition to this free CFT, there is a non-abelian Besdemino-Witten-Coset model, which I will not delve into more than that. But I am about to close. So, so this is the the final CFT, right? And also we could I anticipated we can compute the distance that leads the RG flow to this final point, and it is indeed infinite, but it is infinite precisely proportionally to the time along the RG flow, in such a way that the anomalous dimensions of these higher spin currents that are indeed present in this free CFT because it's free, these anomalous dimensions are exactly exponentially suppressed in this proper distance, according to my calculation. And you see, this is, again, a non-trivial thing, because it could have happened that this could have been square root of delta, right? But it's not. It's exactly delta. And again, this only happens because the exponent match, because this is a string and not a higher dimensional extended object. So this, again, I want...
Ivano, sorry, just understand. So what is the coupling that is becoming free here? Because, I mean, if you have a higher spin symmetry, you are going to have a free point and a gauge coupling going to 0 in the CFT. So
Right. So this final CFT1 is essentially it's a free SCFT, right? Together with the decoupled Westermann
So
itself.
I mean, this operator, I mean, what is the coupling that is associated?
Right. So the decoupling is essentially the fact that this was a nonlinear sigma model becoming free, and the coupling itself is this. It's the graviton vertex, right? You could call it. It's the deformation of the target space metric of the nonlinear sigma model, and in the infrared, this becomes free due to Ricci flow, right? The renormalization group flow becomes Ricci flow in the infrared, and the anomalous dimensions are these ones in the infrared.
Because
And
how many dimensions is this? This is 2 dimensions?
2 dimensions.
Okay, so in 2 dimensions, it's not necessary, yeah, that you have a free point whenever you have a higher spin symmetry.
Correct.
But you are saying that you still have it anyway, or
you still have a free. Oh, sorry. You still have a free sector, but it's also the theory is not completely free because it has this Westermann-Witten Coset model. So it's a free sector plus this Westermann-Witten Coset model. So the theory is partially free. So it does happen anyway, as I say. So according to your discussion in your paper, this is what happens.
yeah, because by Maldas-Nassy Voidov, this only applies to dimension bigger than 2.
Yeah.
Okay.
So it could be different, but it is actually free in this case. And indeed, it ties into a possible description of this. So this theory looks like the worldsheet theory of a heterotic string with worldsheet supersymmetry, which means that it's a candidate for an S-dual theory, but maybe I should just keep this last part. We can talk about this if you like, but essentially this theory looks like a candidate for an S-dual heterotic description of this orientifold model because it features worldsheet supersymmetry and is an infinite distance limit. And indeed, we did a very quick check from the EFT performing the very brave S-duality transformation gives you an effective potential that would be reproduced by this kind of CFT with 2 decoupled sectors. So there are hints that this infinite distance limit could describe an S-dual frame. So this is everything. So yeah, this is a summary of what I told you. These are the punchlines. So the gravity side tells us the space-time likes to close off at finite distance because there is no asymptotic Minkowski. The brane interactions look consistent, and they look consistent with lots of swampland conjectures that arise naturally in this context. So this is what I wanted to say. Thank you very much.
Okay, so let's thank Ivano for the nice talk. Are there further questions?
One question in this last part, I missed why you get supersymmetry on the 2-dimensional theory. So can you explain more about that? Is this an accident, or is there some intuition why it should be the case?
Well,
or it was unexpected.
So you see, we have 2 different orientifold models with D1 branes, and so we could perform this analysis, right, of this RG flow all the way down to the final point in both cases. Now, the O prime B mod, the 0 prime B model, ends up in a free CFT, but it's not supersymmetric because the model itself started non-supersymmetric. So nothing wrong with that. Now, the type 2B orientifold, the one that has a spontaneously broken supersymmetry, there was no guarantee, but it ends up in this supersymmetric superconformal field theory because the fields that decouple and become free are scalars and chiral fermions, and they have an index which is due to the spin 8 global symmetry of this theory, which is the isometries of the transverse directions to the D1 branes in 10 dimensions, right? 10 minus 2. And, and the reason why they build actually 8 West-Zumino multiplets is precisely because of the trigality of spin 8.
I see. Okay.
And this would not have happened if this weren't a string. If it was a brane of higher dimensions, this could not have happened.
Mm.
And we would not have recovered superconformal invariance. And this could have not been a candidate for an S-dual description. And also this would not have been at infinite distance. So you see, everything fits together.
Okay, thanks.
Welcome.
Any more questions?
Looks like there aren't.
I think there were.
But I do appreciate the numerous questions that we had during the seminar.
So is there any conjecture that is left to check in these setups?
I'm sorry, is there what to check these setups?
Any conjecture that was left to check?
Right, because again, we checked the deceptively conjecture, the weak gravity conjecture, all the various incarnations of the distance conjecture, which is probably the most important. I would say that the Transplanckian censorship has to be checked. This is perhaps one of the weakest in some sense, but it is testable actually, because sorry. So the geometry sourced by the 8 branes, right? This is the static Dudasmara geometry, has a cosmological counterpart. You can find it by weak rotation essentially, and this was done in their paper. And it's the simplest cosmology you can find in these theories. And you can just take that and check whether the TCC is valid. This is the first thing that comes to mind.
I was also wondering this distance that you compute in the CFT. Yeah, to what extent is then the same distance that John Stout is using, or?
It's to my understanding, it's exactly that. It's exactly the same distance. So originally I took it from the proposal by O'Connor and Stevens. It turns out that Anselmi did a similar proposal, not quite identical, but similar. And then John, with his paper, very clearly, described these metrics in a modern language, and it's the same thing actually. So I'm pretty sure I computed exactly the same metric, and what I did was, instead of computing the full metric in the whole space, I pulled it back on the RG flow, right? So I computed it along the tangent vector to the RG flow, and then computed the integral. What I only computed this last part, first of all, because this theory is perturbative here, right? Because it's a deformation from a free theory, and and because I only cared about whether the distance was infinite, right? So you only need the final part. So this is what I did. I think it's exactly the Stout metric, if you call it that.
Okay.
So you can just take this vertex operator and you can compute the correlators of that, right? And then integrate, which is what I did. And then you can actually match it to the anomalous dimensions as well.
Yeah, that's nice. Okay, so if there are no further questions, okay.
I have one question. So very quickly, so when you nucleate bubbles, between which kind of Tuvaggia you're interpolating, or what is the picture, or do you have this? I didn't get the details of that part.
Right. So I'm so sorry. So the bubbles nucleate between the ADS vacua that are sourced by these branes. So the near horizon geometries sourced by these branes are ADS times S compactifications, and that have a certain flux, which is proportional to the number of branes. And this is where branes nucleate. And they interpolate between ADS times s with a certain value of n, and ADS times s with a lower value of n.
But you have the solution in the supergravity in the gravity side of the interpolation.
Yeah. Oh, you mean the full profile?
Yeah, I'm worried about the internal dimensions. What happens there? So how is it?
What happens is that there is a back reaction on the radion, right? So the radion mode also changes web. So the analysis, full profile of the interpolation, we studied it in the thin wall limit essentially, right? So the full profile we don't have, but the thin wall profile we have in 10 dimensions. So we included the back reaction of the internal dimensions, if that's what you were worried about.
Yeah. So, but then the branes are not localized internally, or what's
No, indeed, they are smeared.
Ah. So you need to smear to get the solution. Okay. So it's okay. And what if you don't?
Sorry.
What happens if you don't smear?
If you don't smear, or if you do the smear?
If you do not.
If you do not, well, I expect that the ADS picture doesn't change, but the internal dimensions excite higher Kaluza-Klein modes. I think that's what happens, because there is no, spherical symmetry.
So I'm actually worried that since you don't have a scale separation, you are not entitled to smear. That would be my concern.
I see.
Yeah, that's a good point.
It is a good point indeed, and we tried looking at that, but the the full equations are quite complicated.
Okay.
But yeah, I do expect essentially that the internal space, since there is no protection, so it could stop being a sphere, right? Instead of just exciting the radion, it could, the point-like source would distort it.
Yeah. Okay. So I was simply curious if this, as you say, happened, you cycle Kaluza-Klein mode, you go something that is not a sphere because you have a privileged direction or something like that. Which kind of things you get? No, because we are so used to these sphere solutions that we are not used to something less symmetric. And I was wondering what could be going on, where you could go.
We would need to study that more explicitly to actually see what happens. But what I can tell you is that the actual ADS times internal space solution continues to exist for any Einstein internal manifold, provided that the Ricci scalar has a certain value. So indeed, the sphere, as long as the sphere deforms to an Einstein manifold, we are safe.
Okay. Thank you.
That's a very good point indeed. Yeah.
Okay, so if there are no further questions, let's finish here and thank Ivano again for the talk.
Thank you very much. Thanks a lot.
Thanks a lot.
Thank you.